Okay, so now let's give a proof of Atiyah-Bott fixed-point formula. Okay, so let's recall the setting was like this. We had this elliptic complex. To start with, so this was C infinity of 0, C infinity of 1. And say, so the differentials, or I mean the operators here, we call them D. So it's an elliptic complex. That's one thing. And then we had a map phi from M to M. So this is a smooth map, right? So this map had the property that all of its fixed points were simple. I call it non-degenerate, but you can call it also simple. It's simple fixed points. So simple really means that this differential of phi at M from tangent space of M to itself. So you're looking at this map at fixed point. If you look at this map, so call this Tm, then this map Tm has the property that the determinant of 1 minus Tm is different from 0. So that's the condition of non-degeneracy or transversality. So we have that. Okay, so so we had two quantities to play with. One was a global quantity, which was the Lefschetz number. Also, let me assume. Yes, consider the Lefschetz number. Okay, so now, before that, so I'm going to actually consider the action of this guy. So let phi star. We looked at this map, C infinity of EI to C infinity of phi star of EIs. And then we fixed maps, vector bundle maps, say Ci or C from phi star of EI to EI. So these are fixed bundle maps. Of course, they give us also maps between sections as usual. Gives us maps. Again, I call it C from C infinity of EI to C infinity of EI. So this you always have from phi by pullback. This is what we discussed last week, pullback operation. This you have to assume as an extra structure. Assume such maps exist, and then you can use it here. You can compose with so we get maps from C infinity of. So this composition we called it F. And we postulated that this F be a morphism of elliptic complexes. In other words, it's just a morphism of elliptic complex. So also assume that F is a morphism of complexes. Right? Okay. So then the Lefschetz number so L of phi and C, it's like the Lefschetz number of endomorphisms of complexes, algebraic, linear algebraic Lefschetz numbers that we worked at the beginning of this Lefschetz fixed point formula. So this is, by definition, is sigma minus 1 to the power q, trace of f star going from the cubed cohomology of E to itself. You see, because we are over a compact manifold, these cohomology groups of elliptic, and because we have an elliptic complex, we prove that these cohomology groups are finite dimensional. So this F star acts on cohomology. These are finite dimensional vector spaces. You just take trace, alternating sum, and that's. So and we saw that, for example, Euler characteristic is a special case of this gadget, this construction. So we have the Lefschetz number. This, of course, depends now on this homeomorphism phi and also this bundle map C. So the theorem of Atiyah-Bott, the formula is the following then. Atiyah-Bott formula says that this number, L of phi and C, is equal to the sum over all fixed points. And this condition, as we discussed, immediately implies that there are a finite number of these fixed points. They are isolated. Each fixed point contributes a number, contributes a value. So the contribution of this fixed point is minus 1, again, summing q from 0 to now minus 1 to the power q, trace of Cm from EQ going to EQ. This is at n, this is at n. You see, if you look at the cubed bundle, it has a fiber over n, over the fixed point. And you look at this map Cm, acting, sending that fiber to itself, and then you look at this trace. So this is a very particular kind of. And then divided by the determinant of 1 minus Tm, and then we take absolute value. We took absolute value. So that's the formula. This is equal to that. So of course the corollary was that, you remember the corollary that immediately you get, and it's quite useful, is that if Lefschetz number is different from 0, the map always has a fixed point. So the corollary was that if L of phi C is different from 0, then there exists at least one fixed point. So we have at least one fixed point in this case. So that's good to know. Okay, so now how this is done. We kind of started actually last week in the proof, so let me just sketch and go through the proof quickly. I'm just going to give the highlights of the proof. So this is a statement. Now I can just maybe give things about the proof here. So first of all, we have to use this Hodge decomposition theorem for elliptic complexes. So Hodge theory, as we proved, for elliptic complexes. I hope I'm not out of this. Okay, for elliptic complexes. This implies that the Qt cohomology group of E is isomorphic to the space of harmonic sections of Q. This is my notation for harmonic sections. So harmonic sections, the Qt harmonic section. So this is harmonic sections of EQ. Right? So this is kernel of delta Q from C infinity of EQ to itself, the harmonic section. Okay, so, and then we discuss this PQ from L2 to this space, L2 of EQ to harmonic sections. So this is orthogonal projection. This is the orthogonal projection. And we said that this trace, trace of the map that appears in Lefschetz, because of this isomorphism, can be expressed as a trace of the composition, as an operator trace. So let me write it here, the statement. And trace of, oh no, this is the not operator trace. This is usual endomorphism, finite dimensional trace of F star from HQ star from HQE itself is equal to trace of. So we just compose F star with PQ. F star. Now, this is an operator trace. This is just this is also operator trace, but it's an operator on finite dimensional space. This is not difficult to prove at all. I mean, this is just cutting down. Well, I mean, this is a finite rank operator. This is a finite rank operator, and for finite rank operators, you can compute the traces by looking at the images and cut down there. So this is. But the thing is, now we are going to write, because it's kind of on this Hilbert space, we're going to use a kernel of this operator, delta Q, to write a kernel for this, and then start the computation from there. So, so that's the first thing. Now, a similar proof. I mean, it's completely similar as in McKean-Singer formula. This tells us that we can write these alternating sums of traces as traces of heat kernels. So this is the thing. So sum minus 1, I mean, that's not heat kernels, that's heat operators. Minus 1 to the Q trace of F restricted to, I mean, F going from star, going from HQ to itself. I mean, this is, remember, this is the whole Lefschetz number, right? this is equal to sum over q minus 1 to the power q trace of f e to the power minus t. Remember, in the case of McKean-Singer, this f was this identity operator, and we just had left-hand side was this Euler characteristic of this elliptic complex, and right-hand side is alternating sums of these heat operator traces. But the point is that this is true for any t. You see, the left-hand side is a constant. The right-hand side, individually, these terms depend on t. But when you take alternating sums, it's totally independent of t. So this is like a magic formula, but I mean, this proof was quite easy, and but its observation, of course, was very, very interesting. Okay, so the alternating sum, the total sum is independent of t and is given, gives the Lefschetz number in this case. Okay, now, so let's compute first. Okay, so now we want to compute these traces. We know that this is a trace class operator. Actually, it's a smoothing operator, much better than trace class. It really sends all the two functions into C-infinity functions and all that. So to compute this trace, we just have to compute this kernel of this, and then we integrate the kernel over the diagonal. That's what we will do. And that's the technique that we're going to use. So first then is we have to compute the kernel of this f e to the minus t delta q. That's not difficult. So first let's assume that, let's have a notation for kernel of e to the heat operator itself without f. Let k, so my notation is ktq of m1 and 2 be equal to kernel of e to the minus t delta q. Okay, this is the kernel that we know exists. So then kernel of f e to the minus t delta q is equal to, so its value over the point m1 and 2 is given by, so the notation is this, C1, yeah, this is a K, T, Q, phi of M2, so phi of M1, M2. So remember where this kernel lives. I mean, let me just, the kernel lives in tensor products of two fibers, right? So let me just. So remember that, recall that kernel E2 and 1 and 2, this really belongs to, I would say, E over M2. So the kernel maps the fiber over M1 to fiber over M2, or fiber over M2 to fiber over M1. So this belongs to E M1 tensor E M2 star, and this is Q. Okay. Okay, so this is our notation, And now this operator, I mean, this is kernel for this is okay. The kernel the modification of kernel as a result of this f. There are two things, because f, remember, was Xi composed with this phi star. So the modification comes in two parts. First part is that it modifies this variable, and then this Xi1. Xi1 means that Xi is only acting on the first leg. That's what it means. So what you have to do, you can go through the definition of kernel and verify that this is actually correct. So this is, you have to convince yourself this is correct. You sit down and you can convince yourself that's purely algebraic at this stage. Okay, so that's that kernel. Okay, now what we have to do, we have to integrate this guy over the diagonal, right? So, but then we have to use something. Now, the asymptotic expansion of hit kernel so this we know how it looks like, at least the first order term, we know what it is. So this is KTQ of M1 and M2 is equal to, well, I mean, this is, yeah, it's 4 pi t to the power minus M over 2 exponential of minus distance of M1 and 2. Oh, this is dimension of M, by the way. M1 and 2 squared over 4t. There are infinite number of terms. It starts with a term which we call A0 of M1, 2, and then there is another term which I think I call it O of t. So this we know by on general ground. I did not prove this result, by the way, yet. I will give a proof. But there is some valuable information here, which is this. A0 of Mn is equal to identity. Because these are operators, obviously. Because this goes from, we see, from EM2 to EM1. So if M1 and M2 are the same, so okay, so this is a very valuable information. I mean, this really implies Boas law. So this is extreme, already zeroed over the term. If you know it on the diagonal, this is extremely valuable information. Higher order terms, luckily in this case, we don't need. And one comment is that, so it looks like I'm using, I'm dealing with a special case where the order of these differential operators are 1 because I divide by 2 dimensional. Otherwise, I have to divide by this 2 by d. So this is one thing, but that doesn't matter. I mean, you can adjust this to general cases, but this is okay. So using this, then we can just write down a kind of local form, I mean, of this new kernel, which is modified by this phi and Xi1. Okay, so the modification now is like this. So Kt Q of phi of, say, M that is equal to 4 by t. minus dimension of m over 2. Now there is identity here, right? I just take identity here because I'm on the diagonal. So on the diagonal, kernel of well, this operator f looks like this, basically, and e to the minus. So I have to put here e to the minus. So that term does not disappear. That term gives me phi of m and n. You see, if phi, I mean, if you didn't have phi, and if you wanted to look at on the diagonal, this term would disappear. It would be 0. And exponential of 0 is 1, so you stop. But here it doesn't. Gives me this contribution, which is, so I would say distance of phi of m and m squared over t, and then times some terms, times 1 plus some higher order terms in t. Okay, so that's the thing. Now, so we have to integrate this. Now, something interesting happens. So, over m, this, C1, ATQ phi m, and the volume of m, okay, so now, so the idea is this: we are going to use the fact that the sum was independent of t, but individually, each of those sums depend on t. So what we do, we will look at the short time limit of those terms as t goes to 0. So a study limit of this, and its limit t goes to 0 integral m c1 ATQ phi m volume of m. Something interesting happens. Points which are not fixed points in the limit, they do not contribute anything. The contribution goes to 0. So here is your manifold, for example. And you have some distinguished fixed points, some fixed points. So you can divide your integration into two pieces. First of all, small balls around fixed points, and then away from fixed points. Now, away from fixed points, phi of m stays away from m. This is a non-zero contribution around that. And so you don't get 0 here. You get a rapidly decreasing function as t goes to 0 here. I mean, here. If phi of m is different from m, you get a contribution from this term, from this exponential minus, so that rapidly goes to 0. And this term does not contribute anything. So on the limit, this thing goes to 0. So the integral really quickly localizes around these points. So for any small ball, you can show that integration is equal to integral over this small ball plus negligible parts which are outside. So this is the nature of this Gaussian. Now, once you localize, you are near those, so away from fixed points, you can show that this term is very small. So we can neglect it, and it doesn't contribute. And around fixed points, we just choose local coordinate charts around each fixed point, and then we can compute this integral as bring this integral to the tangent space at that point, and use some results about Gaussian integrals, because after all, this is a Gaussian form of Gaussian stays. So what we need is a computation for the Gaussian now. So use so this is a lemma which is about Gaussian integrals. It's this. So imagine you have an operator so it's such that the determinant of 1 minus t is different from 0. So imagine you have a matrix whose determinant is different from 0. 1 minus t is different from 0. And then what we have is that integral of the Gaussian minus, oh, okay, so the integral actually, so this is 4 pi t, the whole integral, 4 pi t minus n over 2 integral over Rn exponential of minus so norm of I would say absolute value of x minus tx squared, or norm of this guy squared, divided by 4t, and this is times dn of x. Yes. This is equal to 1 for all t positive. So proof of this is very easy from what we know from Gaussians, basic Gaussian integrals. Proof for any A positive definite matrix, right? We know that we know what is the value of the Gaussian is, integral exponential minus 1/2 ax and x dnx. You remember the value of the Gaussian?
Not 100%, but it was the determinant of A up to some like 4 pi factors,
right? Is it in the denominator or numerator? And is it the square root or not?
It's in the bottom one? The denominator?
It's a denominator, yeah. It's the determinant of square root of 2 pi over A. So that's one way to remember this. Okay. So anyhow, so this, and now you can use this matrix 1 minus t transpose. So then let A be equal to 1 minus t transpose times 1 minus t. This matrix. This is a positive definite matrix. This matrix is positive definite, and yeah, that's what we take. And then fit into this, and then just okay. So this is elementary now for us. Okay. So now what happens is that, so this is always 1. Question?
Why doesn't the value of the determinant of 1 minus t matter?
Why it doesn't? Oh, it does matter. Sorry. Yeah, this is 1 over 1 minus. So that's sorry. Thank you. Determinant of 1 minus t. I would say absolute value. Yeah. Sorry about that. That's a very good point. So let me check actually. Yeah, absolute value of determinant of 1 minus. Of course, square root is taken care of by this and da da da. So this is everything is fine. Also. Okay, now now that we know this is 1 over absolute value of determinant of 1 minus t, we can compute this, as I said, these integrals over these small neighborhoods by going into the tangent bundle, the tangent space at that point. But also we can kind of cut down and just see the following thing now. Okay, so this integral is over all of Rn. But what you can do, you can just see that if you take a small ball around the origin in Rn, so that it's covered by this under the exponential map. So there is this exponential map covering this kind of geodesic neighborhood of your point here, right, on the manifold. This is Rn. This is the coordinate system you use exponential map. So to calculate this integral, when you pull back, you're back to an integral here, not over all of Rn, and that's potentially a problem. But it doesn't matter because this integral really localizes at 0. In other words, if you divide this integral, the Gaussian, over Rn as integral over this ball of epsilon plus integral over complement of the ball of radius epsilon, this goes to 0. It doesn't contribute. So the integral that you want to compute eventually can be calculated by using these small pieces, localizations of these small pieces. And well, there it is. Now that determinant of, well, not determinant, I mean, the trace of C1 comes into the game because there's a modification here by C1. So then you have it. Everything on the right-hand side appears from this local analysis from a simplified analysis. So all you need to prove this result is just a first order, is enough to know the leading term of this asymptotic expansion. That's all. We didn't have to know anything else about other parts of the expansion. So leading term of the asymptotic expansion is this Atiyah-Bott term. So there are some details that I did not cover. So these details you can read in Rowe's book. John Rose book, great book, as I said before many times. John Rose book, or Gilkey. Gilkey is more elaborate and gives more general cases of the theorem, but Rose is very concise and very slick, very well written. You can easily digest everything there, so you can check the reference. Okay, so that's the thing, and I gave one example already, so let us look at that. Any questions? So I gave one example already, so let's look at that example. So what was that example? That example was the case of the Rome complex. We took the Rome complex for that case. So let me just look at that case. Call our first example. So we had this phi from M to M, smooth, with simple fixed points. And we define the Lefschetz number of these maps sum minus 1 to the power q trace of phi star from HQ theorem of M to itself, right? So we just took these traces, and there's no C, nothing. It was just these traces which is defined. And the theorem, Atiyah-Bott, in this case, implies a classic result. I believe this is due to Lefschetz and Hoff. So this gives Lefschetz. It says that indeed the Lefschetz number of this map is equal to sum minus 1 to the power q sum minus 1 to the power q, and then we have got sine of sum over phi of m equal to n, sum over fixed points, and for each fixed point you took sine of a determinant of 1 minus Tn as it goes from this tangent bundle itself, right? Sine of the determinant. So yes, I mean in this case there's some simplification and just the sign of the determinant contribution remains at the fixed point. So the proof of this, of course, I mean, just wanted to make sure that, yeah, okay. So the proof of this, I just boiled down to linear algebra, right? Proof used the identity, has many applications by the way, which is for any map from some finite dimensional vector space to itself, we said that sum minus 1 to the power q trace of hq of A going from hq of B to itself, q from 0 to dimension of V is equal to sine of, yeah, we use this result that this is equal to, determinant of 1 minus A. So actually, it's on the nose, not sine, determinant of. Okay, so this is a purely linear algebra identity. So to prove of this, we said that, okay, if we prove it for diagonalizable operators, it's enough because diagonalizables are dense. And why diagonalizables are dense? Can you give me a quick argument? Why diagonalizable operators or matrices are dense inside the space of all matrices? Yeah, so, right. So I think our argument was something like this. We said that, okay, so let's prove, for example, that all operators matrices with distinct eigenvalues are dense. And we know that matrices with distinct eigenvalues are diagonalizable. Because if you look at the Jordan forms, there are no Jordan blocks. Because if there are Jordan blocks, then there should be some multiplicity, but there are no multiplicities. So that's okay. So then, so why operators with distinct eigenvalues are dense now? Why those operators are dense? You can imagine if you have a matrix. Okay. So for that, I think you have to write down this discriminant because there's a condition for a polynomial to have multiple roots or not. The discriminant has to be 0 in order to have multiple roots. That's the condition. So if you write down the discriminant, you're cutting down a submanifold inside a space of all matrices. So the complement is going to be some open subset. This codimension of that space is at least 1. So the thing is going to be dense. Okay, so there are different arguments you can do. And all of them are, show that one way or the other that this is dense. Maybe there are even easier proofs. Okay, now what we want to do next is actually give a proof of index theorem. So now we have to, well, we can do several things now. So let me just give the idea of proof what we want to do next. So the idea of proof of singular index theorem. I mean the heat equation proof. Heat equation proof of Atiyah-Bott index theorem. So the idea of this proof is the following. It's really McKean-Singer. So let's, to be concrete, let's look at a special case. I mean, consider for the wrong complex. So we have this Duran complex now, which is omega 0 m, omega 1 m, d, n m 0, 0, right? This is d. So we have got this, right? And so this is an elliptic complex, right? So this is an elliptic complex. So we can compute its index, which is Euler characteristic. So index of this, say, E is equal to Euler characteristic of this M, right? Well, I mean, this is alternating sums of dimensions of cohomology groups, which are Betti numbers. Okay. So, but then in this case, we have Gauss-Bonnet theorem. It just says that when dimension of M is equal to even, then this number, index of E, is equal to some constant, Cn, integral of a very specific term. There's a term which is Pfaffian of some curvature matrix of this over n. So for dimension of, so this is a scalar curvature, k, actually, Gauss curvature or scalar curvature. If n is equal to 1, or n is equal to 1, and more complicated expression in curvature for higher terms, which we will see. More complicated expression, but this is only curvature because this is the Riemann curvature tensor omega that appears here. It's a 2n by 2n skew symmetric matrix, contains all the curvature information, and you take its Pfaffian. More complicated expressions in curvature. Okay, so that's what actually, so this was known before Atiyah-Bott, and this is Gauss-Bonnet. Now, what we want to say is that, well, of course, this follows from Atiyah-Bott, but we want to see how we can prove it. Well, the path to prove this would be to use McKean-Singer. So then use McKean. So first, what does McKean-Singer tells us in this case? This tells us that index of this operator E, chi of M, which is index of E, is alternating sums of operator traces of heat traces, right? So that's equal to sum minus 1 to the power of q trace of e to the minus t delta q, the plus n of q. Q. So this is for any t positive. This is really Laplacian on Q forms. I mean, that's a standard Laplacian, Laplace Bernoulli operators on Q form, nothing abstract there. So, what is the idea now? The idea is like the idea of this proof of Atiyah-Bott. Now, what we're going to do, we're going to show that we can say something about these terms as t goes to 0. So we're going to compute those terms as t goes to 0. But unfortunately, in this case, something very much more complicated happens. Let's see what happens. Okay, so then for each q, we have this, of course, term, trace of e to the minus t delta q is equal to integral this kernel, k t q of xx, the volume of x. Right? And this kernel, we know how it looks like. Kt q of xx is equal to, I mean, asymptotically equal to 4 pi t, for example. In this case, indeed, it's 4 pi t to the power minus n over 2. And then there are these terms, a0 xx plus a1 xxt plus a2 xxt2, so on, right? That's what we get. Okay, so now we have to decorate these a0s because they also depend on dimension q. So I put q here, q here, q here. So if we just carry out the alternating sums, then we get something very interesting. First of all, it should be 2n here, right? So I just put minus 2n, right? The dimension. So they simplify, it gives me minus n then, right? So something interesting happens. If you take alternating sums of these guys, so integral of alternating sums of these terms now is equal to this chi m. So this is for any t, right? This is for any t. This is for any t. Now, well, what happens, because this is a constant and there is a t dependence here. And these t-dependent terms cannot be absorbed, cannot be killed by this power of t. It gives you trouble if these terms, these integrals are not 0 for up to term anq. So all integrals, so what should happen is that, what this certainly says happens is that for all I less than n, we have this, I mean, these terms have to be 0. So this is integral sum k, so I would say ai q, I mean, minus 1 to the q, like this sum. Minus 1 to the q, aiq xx, the volume of x. Okay, yes, q from 0 to n. It should be 0. And At the nth term, so that's one thing, that's for all I less than n, bigger than or equal to 0. And for I equal to n on the nose, at this term, minus 1 to the q, a n q xx, right? The volume of x, is equal to an index of your operator, chi n. So what? So you see, that's what happened. So what the McKean-Singer kind of conjecture is that this might give us a way of arriving at the formula by the following method. We can compute these terms because these are some expressions in curvature. And then if you're lucky, we can do this algebra. If you're good enough with algebra, these curvature terms, we can compute these terms. And maybe these terms also will cancel. I mean, we know that they should cancel. But the thing is, cancellation here and the formula here, it's only after integration. So what they conjectured, it was that maybe even before integration, there will be a cancellation here. So they call it, because I mean, we have integral of some alternating sums of expressions is equal to 0. It's one thing to say that, it's another thing to say that the integrand's alternating sums are 0. So they call this magical cancellations. So maybe magical cancellations happens here, and maybe magical cancellations actually happens here also. And this monster term, I'll tell you why this is monster. So this monster maybe magically simplifies, because we know it should simplify. But the simplification is even before this integration. I mean, it's not that we just get some expression whose integral is the same as integral Pfaffian. We want to get something on the nose that's Pfaffian. So now, why this is a monster? Look, the expression here, it's true, this result, what Gauss-Bonnet theorem proved by Chern and Underway and others before Chern, is that this is true for any dimension. For any dimension, you have a universal expression in curvatures. So that expression is known, was known. But these expressions, the heat coefficients, only has been computed up to order 6. And if you go to order 6, already you have, I don't know, maybe 10 terms. If you go to order 8, you get like 20 terms, and it just explodes. The number of terms explodes. And beyond the term number 10 and 12, there's no formula. So we have no information about this term. So this looks like a hopeless task to do, because we are reducing the problem to something which even is more complicated. It's even more complicated because each term cannot be computed. So that's why they were hoping for some magical cancellations, so that without knowing the exact forms, maybe by some magic, by some trick or something, you can cancel, because all we care is alternating sums. We don't care about nature of each term individually. And that's what actually happened. So that's what happened. So what we're going to do, so there were different proofs then. So there was, okay, several people, and I cannot list all of them, but certainly give a proof along these lines with some invariant theory. And then Atiyah-Singer gave proofs along those lines. There were several other people who gave proofs. And then there is a proof due to Getzler. I think this is around 1985. This is done in this book by John Rowe. So Getzler's proof, it's kind of quickest, nicest, in a way, beautiful proof. Works for Dirac operators, and these guys also did it for special cases for Dirac type operators. So I'm going to use that proof. So we'll give details of that proof. So this is a very, very, very important proof. One more comment is that in all these proofs, with this heat equation proof, you can never directly prove the theorem for all operators. This is never the case. You always prove the theorem for Dirac and generalized Dirac type operators, and then you use some sort of K-homology argument to derive it for general elliptic differential operators. Because you notice that if you twist these operators with arbitrary vector bundles, then you can generate at least homotopically all operators. So there is some sort of K-homology argument that but the crux of the matter is really to understand this proof in the case of Dirac operators. So I think what we're going to do next is spend some time understanding Dirac operator, the gimmicks of the Dirac operator, or maybe I should say the yoga of the Dirac operators instead of gimmicks. And then we can then just give the proof. So yeah, I mean, you can read ahead in John Rowe's book or Gilkey's book, and also there is a book by Berlin Getzler-Wern, which is a beautiful book. You can just read it there. So I think I'm going to stop now. Any questions or comments?
So for I bigger than n, we don't know anything because those terms vanish in the
for I bigger than n, they definitely vanish. They definitely vanish. But we don't need them, right? Because it's like if t goes to 0 already, we know that they are going to 0 because this power here dominates. This negative, the positive power dominates the negative power, so they just go to 0. So the limit t goes to 0 is not, at least the way I see it, is not informative. So the things that matter is do the proof. Well, I mean, even this is not important. This is important because we know that this cancels anyhow by the general thing. So what we should focus is to find this term. That's all. That's where magical cancellation happens because, I mean, these terms really are like, if for example, if n is 10,000, there are millions of terms here. It's outrageous, you know, it's outrageous. And it doesn't matter. It gives you a kind of short formula, which you can control. So this is really, yeah. Okay, so any other questions? Okay, so I can stop the, Jeremy, you have questions?